Welcome to my talk on privacy-preserving models for legal natural language processing. This is joint work with Ying, and my name is Ivan Habernal from TU Darmstadt. Let's get started. So we are introducing our approach by this example. So imagine you have a GPT-2 model, which is a generative model, and what we're expecting for such a model is that if we have a prompt, for example, here English, what's the time, German, we want it to translate, translate to German this sentence. So perform a downstream task. So it's intended behavior. However, if you're an adversary, so the bad guy, and you prompt it with some adversarial prompt, what this model is going to spit out is something which is undesired. So for example, GPT-2 model can spit out unique names of individuals, addresses, emails, phone numbers, unique URLs, and so on. So even if these things were seen only once during the pre-training of this GPT-2 model, and this is somehow an unintended behavior of such transformer models, and the problem is that many contemporary deep learning models kind of neglect privacy. When we go to model publishing, so for example, here we have a general data set of just a very small data set of 3 persons in there, and what we typically do is we train it using stochastic gradient descent, and we have some model which we publish later on. So the model is basically an architecture and a bunch of parameters here. So if there is an adversary, a bad guy, and also when we leak some other data which doesn't contain LEs, so we want to protect LEs here, for instance, but we have data sets which is leaked from Bob and Charlie, the adversary can also train a model, maybe the same model, and then just basically seeing the difference of the trained models, he or she, the adversary, can find out whether LEs was in the private data or not. And there are so many other attacks which the adversary can do. So how is it relevant to legal NLP? So what we're doing in legal NLP with language models is that we start with something, some self-supervised pre-training. So we take a bunch of unlabeled documents from general corpora and pre-train a model, for example, the BERT. And then we fine-tune BERT on some downstream task. So for example, here it could be text classification on legal contracts, for instance. However, it's been shown that if you do the pre-training, if you take the BERT pre-training generally and then continue pre-training on domain-specific self-supervised data and domain-specific data using self-supervised training as well, and then fine-tune the model, you get much better results on the downstream task domain. So basically, legal BERT has been pre-trained on legal data, and it gives you an advantage over a general BERT. So this is domain-specific fine-tuning. However, if there is an adversary again and has access to the final model, given several techniques, he or she can really access some private data in the pre-training. So what could be a use case? For example, we want to we want to pre-train the model on domain-specific data, which are somehow private for a company, for instance, or it could be some contracts. And obviously, we don't want this private information to be leaked from the final model, which we can just basically publish for everybody to use, maybe upload to Hugging Face. So what we are trying to do is to use differential privacy for preserving privacy of the final model. So how does that work? Again, we have this data set of LEs, Bob, and Charlie, and we trained it with stochastic gradient descent, and we have the final model here. And now, let's say we trained the model with one person missing in the data set. And again, we would train it with stochastic gradient descent. The idea of stochastic gradient descent with differential privacy is that we add just enough random noise to each of the gradients. And through this, we guarantee that the adversary cannot really distinguish. Well, he or she can distinguish, but the distinguishable capacity is limited, whether or not LEs was in the training data or not. So there is a formal bound on how much privacy could be lost about each individual in the data set. So this has been used for some time now in machine learning or in natural language processing as well. But we are interested in how much can we scale it up to pre-training on large-scale data in domain. So again, our setup is that we have BERT, and then we have a large data set of legal documents, so a couple of gigabytes, and we use self-supervised pre-training for pre-training the model. But for that, we need to use differential privacy. So what we implemented here is that if you use differential privacy in stochastic gradient descent out of box using existing frameworks such as Opacus or PyWiki, it won't scale. So you cannot really pre-train on this large data set. It will take months or years. So we experimented with JAX and kind of re-implemented pre-training of BERT using this JAX, and we can see it really scales well. So there is not much performance loss. And using this, we are able to we are experimenting with a couple of downstream downstream tasks, and using just this pre-training with some epsilon of 5, which is kind of the privacy budget, so the strength of the privacy preservation. The smaller, the better, and epsilon 5 is considered as okay privacy guarantees in the community. We are able to get 2% improvement on case hold classification task. So just to sum up, we did this pre-training with differential privacy, and then the question you might be having is like whether this 2% is really worth the effort, or why even do this, and so on. But given this is like very short spotlight talk, I would suggest you have a look into the paper, and we publish our code on GitHub as well. So thanks, and see you in the question and answer session.